What's up, everyone? Hello. What's up, everyone? Welcome to my yet another stream. And today we're gonna be working on operating system, as it says on the title. So hopefully we're gonna have a good time. And actually I found 2 good resources. And yeah. Okay. So I guess we're just gonna start working instead of waiting for it to work. Yeah. So actually this sound is like kinda good. Oh, my bad. Yeah. So I recently was okay, so let's remember for what I wrote last week. It was org 7 COO. So the floater knows where the first data files I think. And what was it? So we go here and to print the first word, we're gonna space AH 0x0E, and we're gonna move hello to the race for A. Now this is N, the word N, know the pointer. Okay, and integer or int 0 is 07. No, it's 0 is 10. So the computer knows what to do. I mean the BIOS. And we're gonna minus 510 minus 4.7% to be 0. And this DD we're gonna say F5. So I should really remember how to compile. Maybe that's my weakness on this thing. No, I should be able to. We use the wait. I gotta check here. It shows us right now. No. So we're gonna check this wiki. So we can either use the NASM, or we can use the GCC across what do you call it? A cross-platform compiler. So this turn shows using this one. Okay, so it's same, and you can make this binary direct nodes raw. Oh, I missed it. Alright, so this is bootloader bin and beautiful assembly. Okay, so yeah, this is reason for NASM. I think bootloader to bootloader bin. This tray also contains for using NASM. So yeah, let's try with the way how it does it for NASM. There you go. What? Org? What do you mean org? Unorganized directive. Did you want like to specify the dates that they're 16? Still the org. I think I really have to specify that, otherwise I don't think it's gonna work. How to use QMO? No idea. So I'm just gonna go up to like find. Alright. So let's see. The total. It's failed. Bruh. I didn't need to close that video. So I guess we're gonna find alright. Well, X70. Oh, that's how it should do now. Is it works? No, probably not. If you Google it, it's gonna work supposedly, because it doesn't define it here. So yeah, it should have worked, but I don't know why NASM is giving us this error. Okay, or you should change it to NASM is Oregon line 2. No, I was just listening, you know. How about it then? So no, I'm not on NASM, I'm on NASM. So it's the way how I compile it. So like this fixes. Yep, it does. There you go. Emo. No. Yeah, it's been. There you go. I mean, you know, at least that I still haven't forgot it. So now we're gonna follow. Okay, let's see why he's getting this. I think it has to be small letter. Okay, running ELF. Oh, so he's working with the ELF. Yeah. And I'm working with certificate OS. So yeah. Definitely that could be the issue for them, but yeah. So let's just follow this run tutorial. Writing the bootloader master trigger file. Okay, so register from the device into physical memory at the memory address 087000, which we do it here. And okay, in this case it's called the boot sector will hold 512 bytes. These 512 bytes contain the bootloader code, the partition table, the signature, as well as the magic number that is changed by the BIOS to avoid accidentally something that is not supposed to boot sector. BIOS then instructs the CPU to jump the beginning of the bootloader code, initially passing control to the bootloader. In this tutorial, I only mentioned about the bootloader, so if you start missing kernel, it's really because we will not be able to see the code printing system into 500 bytes in order to start our panel. The board model will have to perform this task. Load the kernel from the disk memory, setting up the global descriptor table, GDT, switching from 16-bit real mode to 32-bit protected mode, and passing control to kernel. Great. So, wait. Okay, great. So, okay. Organizing the code base, we are going to write the bootloader in x86 assembly using master. The kernel will be written in C. We will organize the code in multiple files, increase the readability and agility. The following files variable for a minimal setup, and like MBR is the main file of the primary, the master boot record, or the 512 bytes data. So this means this is the boot assembly in my case. It's just too boring. I mean, whatever. I think I've had like a new viewer. It's a stream, you know. It's gonna be used for the video. Okay. This assembly contains code to read from disk using BIOS. Alright, so we're gonna have that. This assembly. DDT setup, DDT. Global descriptor table. Okay. DDT.assembly. Switch 30-bit contains the code to switch to 30-bit protected mode. So every single thing has its own file. Even if you want to switch it to 30-bit protected mode from the 16-bit real mode. So yes, that's how it works. So the kind of okay. But first, let's read the switch to 30-bit assembly. Alright. Current assembly contains an assembler code to hardware to our main function in kernel C. And yeah, I know that. Kernel in free.assembly. And kernel C and the makefile. Kernel C and makefile. Right, that's great. So far so good.
Let's go to the other end. Hopefully it's really nice. It's just that you a long call that the flip on shishi. The girl was on his bike.
So yeah, obviously I know there is some except the GDT. That's what I don't know. So I think the bootloader master bootloader file. The main assembly file for the bootloader contains the definition of the master boot record, as well as includes statement for all relevant helper modules. Let's first take a look at the file as a whole and this is section individually. Alright, so this is the master boot record or the MBR file supposed to be. So we have the 60, we define that is 60-bit, and we tell the BIOS to look for the bootloader at 087000. Yeah. So ready to load the kernel. So kernel is gonna be, I think, on OX in the 1000. So that's gonna be here in the boot assembly. We don't need this. So kernel, what is it? Kernel offset. Alright, so the kernel set is gonna be this is where the kernel starts. The kernel. Alright. So everything is in the same file, huh? So we then first set the boot driver in DL store for the later use. So we wanna store the boot drive at DL. Okay. So we set the boot drive to DL so we can later use it. This and I'll spin. So my bad. So we move the BP to this into the BP and BP to the SP register. So we move what? BP goes 9000 and we move SP to BP, right? And we call the load kernel. Call the load kernel, yeah. Load kernel. And we call the switch to 30-bit, right? Call switch to 32-bit, right? And we jump. It's kind of loop thing, or like keep jumping to. Wait, I gotta take that. Oh bad. No, it's a dude. Alright, yeah. It's kind of loop. So, we include the disassembly. Yeah, there you go. Assembly. We include the assembly, and we then include the switch to a little bit of assembly. Yeah. So yeah, all right. Then we still are in 60 bits. Wait, should we do this on new ending? I mean, it's gonna be an experience, isn't it? Yeah, I think we should. See. And then, and yep. So let's make it a little bit bigger. Right, that's good. So now we load the kernel. So the load kernel contains we move the kernel offsets this value into bx. So yeah, loads kernel. We move the offset kernel offset into the bx. Then we also move here to the DHY each num sector, so the H is the navigating sector and base is our destination, and DL is our disk because drive that's DL here, and I don't know why we have in DL, but should be something. Yeah, so right, yeah, good drive, think, yep, and we call the disk node. Where is the disk node? I don't know, I think we're gonna write that inside the disk assembly, GDD, or maybe in the switch to bits, sorry, bits to assembly, but surely in a disk assembly. So, yeah, all of this. Yep, I forgot what red was. Assembly, assembly. Rate. This two instruction simulate rates. Jump keys. Okay. So now we begin the 16-bit mode. It's supposed to be using one big S file, but I think so. So now we load the 30-bit. So it's 30-bit slider, and we begin. Wait, no. Yeah, no. Begin 30-bit. Oh gosh, I have to go to this one. I gotta change the ending. So now we call the kernel safe. Yeah. No. Then after we call the kernel safe, we're gonna jump in the loop in case the kernel returns. Okay. Yeah, actually that's good. We jump. Yeah, we make a loop. Then we try variables. We drive will be 0. Then the rest is yeah, and this remain. Right? Yeah. So it's 510 because we want it to be 512 bytes, and that will drive 0 and all. Yep. Very good. So the first thing to notice, we're going to switch between 50-bit mode and 30-bit mode. So we need to tell the assembler whether it should generate 50-bit or 30-bit instruction. This can be done by the 60-bit and 30-bits directly, respectively. Here is starting off with 16-bit instruction as the BIOS jumps to the bootloader while the CPU is still in 16-bit mode. In NASM, the org 087C of the directive says the assembler location counter. We specify the memory address where the BIOS is placed in the bootloader. This is important when using label, as they will have to be transferred memory addresses when we generate machine code, and those addresses need to have a correct offset. So the kernel offsets are statement defined, and simply concept called kernel offset with the value of this value, which we will use later on while loading the kernel into memory and jumping to its tree point. Considering the bootloader location, the BIOS stores the selected boot drive in the DL register. We are storing information in memory inside the boot drive variable, so we can use the DL register for something else without the risk of overwriting this information. Good. So, before we call the kernel procedure, we need to set up standby instant pointer, register speed top stack, goes downward, and the BP bottom stack will place the bottom of stack in 9000 To make sure we are far away enough from our bootloader with memory to avoid collisions. The stack will be used, example by call and break statements to keep track of memory addresses, then executing assembly procedures. Now the time is come to do some work. We will first call kernel procedure in the instruct the BIOS to load the kernel from disk into the kernel offset address, and load kernel makes use of our disk load procedure, which we will write later on. This procedure takes three input parameters: the memory location to the place, the read data into BX, the number of registers to the DH, and the disk read from DL. So I think my eyes are kinda hurting, but this thing is not helping me, bruh. It has been done like for quite a while now. I don't even know if it's gonna back up anymore, but I don't think so. So as soon as we are done, we will return the next instruction. Call to switch to 32 bits, which calls yet another procedure that we will write later. Right. Right, I don't even know how I'm gonna spell this. I'm gonna have to write a makefile. I think it's actually good having a makefile. Alright. Yeah. This concludes our main build in order to make the file master builder. Yeah. This is to make it 512 bytes of the bootloader. The BIOS knows what to pick up. So, reading from this rather is the way we're doing in heavy mode, as we can utilize BIOS functionality by sending interrupts. Without the help of the BIOS, we would have to interface with the I/O devices such as address or floppy devices directly, making our bootloader way more complex. In order to read data from this, we need to specify where to start reading, how much to read, and where to store all the data in memory. We can then send an interrupt signal by in0x13. So I think that's what is from the disk. Now this is what's from the disk. So where does it define that? Okay, so I think it's here. It was 13, isn't it? I don't see anything 13 though. You can easily search for it. No. Still no. Paste to. Okay, why do we wanna use the paste to? And when the real, like the modern one, with serial USB, and I think it's kinda hard. Maybe later on we can implement that, but as of my knowledge, there's 13, which only sits up to PS2. It's not good, but I mean, it's not gonna support the modern keyboard with mounts like what's built in on our laptop or our external ones. So the PS2 is for like the very old one. This one we might actually have to get this to actually make the OS work. And so supposedly they are easy because there are two different things. The green one is mouse and it's the keyboard. It doesn't have support like USB or anything. You can just work around with this, but in the modern one, you gotta know if the device that's plugged in is a keyboard or a mouse, or even if it's any thumb driver, HD, or whatever. So yeah, that's what. So number of sectors to reach. Cylinders, a drawing register loaded to buffer address pointer. If there are disclaimers, files should say carry bit. In that case, we should usually show one error message. With our best, since we did not cover how to print this, and we are not going to do this. In this pause, we will simply loop indefinitely. Let's take a look at the contents of this assembly now. So I guess we're gonna be working with the disk assembly now. Alright. So this not bad. This we pushing dx. Remove h to 0 is rated, and we tell it to set us into a read mode. So h002 and L to the edge with the h number of sectors. So we wanted to reach the number of sectors, and move CL 002 start from sector 2. So now when we move 002, it's gonna, I think, be reading, yeah, it was in read mode, so yeah, we're gonna start from sector 4. As the selector 1 is our post sector. Alright, so we wanna move yeah 000 and the way to 00. PL drive number is set as to this load, and yes, BX, these are buffer pointers that is saved as an input as well. So now we enter the BIOS. I think I don't remember what we used. 34. Yeah, it's the driver, I think. No. No. All then 30. Oh, so we're setting it to real mode. There is 3 and jump. I forgot what JC was. Jump it from made. So if it's true, then we jump to this era, and we pop the X. This and compare all in PH, and we jump if not equal to sector dealer, and we call A and rates. So we now work on the distributor. So we jump to this loop, this loop. We can write that later on, and next errors then we then jump to this loop again. This loop again, and now we work on this loop, and that's gonna be jumping loop, right? So the main part of the file, the Devlog procedure, because the input parameters we set in MDR. That's it. We modify to place the read data into BX, and the more features to read from BX. Yeah. Right now we are on the global discovery descriptor recursor GDT. Students will leave 16-bit real mode. Memory segmentation works differently. The mode memory segments are defined by segments which are part of GDT. For our tool loadout, we will set up simple possible GDT which resembles a flat memory model. The codes in the data segment are fully overlapping and spanning the complete 4 GB of addressable memory. Our GDT is started as follows. So a null segment descriptor, which are 8 bytes. This is required as a safety mechanism to catch errors with our code for this to select a memory segment, thus yielding an invalid segment as the default one, the 4 GB code segment descriptor, and the 4 GB data segment descriptor. So this really defines the dips. I think wait, the base so it will be 17 to 20 bits. Length of segment is will be 0.8f for both our segments G, or gradually if the segment is counted as 4996 bytes pace, this will be 1 also. Our segment transforming the limit of 0x 5x page into 0xFFF of bytes, which are equal to 4 gigabytes. The default operand size divided by B or big. Yeah, okay, I see the code. So this is the GDT. Most people don't write their own bootloader, but here I am writing my own GDT. GDT start. So as soon as it starts, we the switcher DQ erase now. Nice erase 0 and GDT code. GDT code. Signaling of bits from 0 to 15. DDO is like the small version of DD, so it's DD. DW08FFFF. That's for F, so DW00, DW8 again, and that's no, it's DD actually. DX0 still. So the basement say the segment base is gonna be bits from 16 up to 23. So we set the DB, the bits. Alright. DB, we're gonna paste and that same, I don't know. No, it's not. Today we're gonna paste and we're gonna set the DB to 00 from 24 to 31. 0 plus the bits and plus for the bits, segment lengths bits. Yeah, so now we get to the DBT data. DBT data and BW 0xFFF. I think it's the same. BW 0x0 DB 00 And we're gonna set this. I think it's the same thing. So I think it's on DD and still DD and right. So now we set the DB to 0. Exactly like the code. Now we end it. This. My bad. This DWGDT end. DWGDT end. Minus GDT start. And still minus 5.1. And that's gonna be size GDT bits. And now the DD is gonna be DDT start. Yep, that'll be it. And so it's gonna start at 30 bits. So yeah, it's couch segmentation, which is DDT start. No, I mean it's good, my bad. And couch, no, it's not couch. It's data segmentation here, which is equal to DDT data. What? No, wait. Alright. I didn't mean to create a new file. We're done with that. I think let's just do no wait, that's risky. I'm gonna do that later. Not gonna create anything. So DDT kill minus DDT start. Okay, so we subtract DDT starts from either of those. Minus GDT. No. DDT starts and yeah. DDT starts. Alright. Okay, cool. So we're switching to persistent mode. Just going to switch to 30 bits persistent mode so that we can hand over to our service area. We have to perform the following setups. Devlog tab using the CLI instruction. Load the GDT register to the GDT register using the LGDT instruction in the persistent mode. In the control register CIO. On jump into our code segment using jump. This need to be hard jump so it flies the CPU pipeline, getting rid of any prepared 60 bits instruction left in there. Set up all segmentation registers. Now I didn't need to click there. DS, SS, ES, FS, and GS. 2.2 hours signal per gigabyte of data segment. Set up a new start by setting the 30 bits button pointer with a EBP register and stack pointer ESP. So we jump back to BPR display and give control to kernel by calling our 30-bit kernel. But now let's translate that into a symbol so we can write the switch to 32-bit assembly. I've been streaming for 44 minutes now. We have had 2 viewers and me. Now let's translate that into assembly code. So we can write switch to 30 bits. Yeah, get the idea. We're gonna be now switching to 30 bits. Real mode, real rotation mode, I think, yeah. So Okay, yeah. Alright, so we wanna be here, and let's translate that to simplicity. Right, shift this, okay, alright, so we first start at sorry. We first start at base 16, then we switch to 32-bit, yeah, then we double all the interruptions, then we load the GDT script up. GDT is and we gonna move the EX to the CR0 to the CX. EX I mean, and or EX OX1, then we move EX into the CR0 and the EX, which I think is gonna be OX1, and we're gonna jump to code segmentation, and okay, what is going on? It's lagging very badly. Oh boy. What? Did it crash? Gosh, yes it did. Oh my god. No way, I didn't save that good. I mean, it's alright though. We can get it back. So I think if you're working on this base mode, please recover if you can. There you go, okay. Oh gosh, there you go, we managed. I mean, it wasn't that much, but still. Now it sucks to lose every bit. Okay, so now we jump to the code segmentation with the 3 bits, right? Now we're really into 32-bit mode. Let's and it, yeah. We're gonna move X to data segmentation. We move this X this X this X that is, so we're gonna be moving to X in general. It's 90,000. 1, 2, 3 things. Yeah, it's 90,000. Move this P, P. Yeah. Then we call make it 32 bit. 32 bit, then yeah, that'll be. Association to the more we are ready to handle very control to our kernel. Please hopefully we can also handle the make file. There we go, yes we do. What? This is what we're supposed to see? Oh, actually, that's really cool. I'm back in the top. Yeah, this is the basic setup. I found so far, yeah. And we have everything installed. Gosh, this is good. This is good. Alright, so where we left off, no, not here. We just wrote this, now we're gonna write out C. Okay, I actually like to write it C. Finally, the high level part. The fucking high level. Oh gosh. We're gonna write in high level. Bruh. Is it gonna crash now? With me. So with character video memory, it's a variable to the video memory has a character pointer to 0xb 8000. Yep, gotta be 8, I think. Yeah, we set the pointer video memory to X. I think we should be saying X and we better do. And I think we're gonna be then gonna write on MBR. Where's the MBR? Oh, MBR is this. Context of very plugin on the units that we still need to call the main function. We don't need to do that. We are able to create a assembly program that will be placed at the kernel offset location in front of the compile C kernel when created the body make the content of kernel assembly. So kernel assembly, where is it? Wait, we don't have one? No, it's 3. So we're gonna start as a bit 32 because it's 30 bits and external. No, it's start. Then I believe, which I believe is the kernel will say the main function, and now we're gonna call the main. Then we're gonna make it. As expected, there's not much to do here. We are only going to call our main function to avoid the recent assembly process. We need to declare main as an external procedure that's not defined within our assembly file. It takes tasks to linker, resolve the memory address of main so that we can call it successfully. It is important to remember that the kernel assembly is not included into our MBR assembly, but will be replaced at the front of the kernel binary in the course of the next section. So let's see how we can combine all the pieces we built. So I think I'm gonna rename this boots. So how I'm gonna do is that we're gonna I think I'm saying the Linux command to assembly, but do assembly to mbr.assembly. Right. So there you go, here we have it. So now we're gonna have a makefile. Yes, we do. Now we're gonna run kernel.speed. Oh gosh, I think I should just copy paste the makefile. I hate to writing the makefile for the reason of knowing, yeah. Okay. Now I think we're gonna use make missing separator. Where are we missing that? So, make run and beam. This everything is separated. Where? Where exactly? This light pole. But I don't see any problems here. So oh, okay. Then I use a single tab. Okay, so like you gotta fix it for every of them. Okay, I should have wrote it by hand. 1, 2. Okay, so like now let's see if it's gonna work. Now it's 7, which means it worked. That's the issue. I don't know where I am. I can't see. Now I do. Make syntax error. Disassembly. So I think it was the very first one, isn't it? No, actually this works. Doesn't it? With the spin. No, not yet. So says that there is an expression syntax error at the line 16 of the assembly. And where did it say? 16. Here. DDT.assembly. What is wrong with it? It says there is an expression error. Let's try to compile it here. So at the MBR it says at line 16 there is an expression syntax error and it failed. DDT.assembly. DDT.assembly. And I don't see anything wrong here. Let's include. Yeah, it's double quotes, space. Actually, no idea what's wrong here. Include DDT.assembly. Yeah, obviously you're gonna STI. No. What? It is correct. So it's GDT.asm. So it is. But it's refusing to work, which really sucks. No. Take your pass. No, it's alright. No. No, it's all the same thing. No. Without work, to be honest. Yeah, same reason as this. So where we here? Oh, what am I even doing? And it's this, isn't it? GDT, no, it's GDT. So what's wrong with it? Why do we think it will make syntax error at 16? No, it says a disk. Wait, did it say a disk the whole fucking time? Did it say disk the whole fucking time in I'm trying? Oh gosh. Yes, it is that disk 16. Oh my fucking god. It was not even a big deal. Now it's it. simple that data set is notifying where in your assembly. Here says the data set is notifying that Lento is empty. Oh no, bro, I'm crazy. What? So, is there anyone? No. Okay. I think I'm wrong. So it's everything works. I mean, let's check it here. System beer. So yeah, and it says Atlanta. The other thing's not found. It says, and it sure doesn't. Now we gotta check how this works. Data sake. Where is data sake? Data sake is actually found, but not data sake. And data sake is defined here at I believe the data assembly data. Oh no. 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 Huh? There is a card. What? Isn't that how exactly the tutorial does it? Let's see. Yes, it is. There. And in our case, this is like, exactly the same. Pointer, video memory, pointer, memory, plus 2x, plus 2x. And it's the same thing. I'm gonna show you guys if I copy the tutorial. It's gonna work. Swear to God. Oh God. Why does everything have to be yoink? Should we ask? Because I don't see anything wrong. How is it invalid? Yes. Not a single car. What is the difference? Single. Oh. Wait. Oh. I've had this issue before. Oh, yeah. That should work. And yep, we do see that. Yep, that's a good sign, definitely. It's gonna have some views. There you go. And could be this like this. I mean, out of all 6 subscribers, who do you think is gonna see it? Yep, we see the X. That's good. Alright. So, yeah, we made it. So, I think now we get a ride on the VGA driver. All participants some way to interact with the user, which requires us to do some stuff. Normal. Okay, now let's remove this thing. Let's remove that. Yep. There. Now, our system is some way to interact with the user, which requires us to do some form of I/O. First, we want to focus on visual output. We all rely on the VGA 80x10 video mode as it's very convenient to handle and flexible enough for basic terminal functionality. This is the same mode that was already used by the BIOS. By putting to our kernel, with VGA we can produce screen output by modifying a dedicated memory region called the video memory. There's in addition to that, there are specified port addresses that we can use to interact with the device port using the port I/O CPU instruction in and out. This is possibly because all the I/O ports, including the VGA ports, are mapped to specific communication. The password for VGA driver will be whatever. Okay. Oh, now we're in business. We're in business, baby. So we're right in here. I think so. It's actually like single byte. So like if I write this, then I think it's gonna. Yep. Just press the last one. See. Okay. So yeah. First of all, we have to like I don't know. Research code of what? Yeah. This was written 5 years ago. Crazy. Time flies, bro. Why are we here? So provided assigned shirt port data, provide out assigned shirt port data, assigned character data. The provided is an assigned character function. So I guess I'm just gonna keep following me here. Yeah. Nice design, yeah. To the pointer, I mean, come on. Yeah, let me see. and unsigned ports, unsigned character results, signed card results, and we're gonna have to write assembly directly in the seek, basic shit, clean, dx, l. Oh, bruh, no. I mean, all I want to do is to load the kernel. Good, okay. So now we need a void for bytes and have assigned are I think outside transport and our data or I mean not car char. It's saying this which means assembly. Actually, this thing is not that hard. As long as you found the right tutorial. Did he crash again? No way. Yeah, I'm just gonna leave this video simple like this. Sucks. I think that sucks. For a powerful function, we map the survival curve into the experience given in L distance to the value of L is to see variable result. The power by functions like survival. This is easily mapping the power PDAs in the data to as we are only running data. There are no output parameters to and the function estimate the value. Within setting the cursor position, with our newly returned program machine, we are ready to drive it. The BGT's cursor mode. In order to do the bridge, change the cursor to position we need to provide the BGT register, which is 0x3d4. 0x3d4 and read down from right to the respective data register 0x35. The base 16-bit cursor position is encoded as 2 individual bytes. The high into the byte, the data register will hold the byte. If the control register is set to the register F, and the high byte is the value. The rest, which is first to find the register addresses and the code for our so that's sequence stats. So we define the DA register the UX3D4 and we're gonna certify the data register to be at UX3D5 and we're just gonna define PGA 6 go to 0x0f and we're also gonna define PGA 6 high and down high is 0x0. Good. So we're gonna set the cursor. Okay. We're gonna get here. Void offset right there. No, this is too big. It's either too big or too small. So we need the offset as a integer, and the offset is gonna be by the offset divided by 2, and output by r VGA control register and VGA offset high, and the first by still out, it's all out. VGA on data register to be outside character at the yeah oh state 0. No, it's not 0, it's actually 8. So we're also gonna send words by out VGA at control register VGA offset lock, and let's figure out the same thing by VGA dispense data register, and it's gonna be inside character at the offset and the rates okay. Right. Good. We're gonna get the cursor ports by R VGA it's a control register, and the assigned character data is gonna be VGA offset high, generally high, and no, we create a variable called offset, and we make it third party VGA data register to be less than 8, and for bytes by hour we VGA control register VGA control offset low, and the offset gonna be adding up with bytes into input VGA data register. Data right, and now we're gonna be returning the offset multiplied by right. Continue calculating the screen. So we're gonna define the video address master elements and define white or black. Alright. It is the base, not one of the base, but the base, literally the base tutorial I found on this topic. Wow. Just from experience, yeah. We can define the video address at the USB 8 yeah, and we're gonna define max rows 5 and define max rows at 8, and we're gonna define lines on back 0. Right. Okay, we're gonna write a new function called void this memory, and the second image would be offset inside page video memory and bar. We're gonna convert the video address onto a car and we may say to the character that is as equals to character and the page made of say plus 1 and it's gonna white and black. Well, that's because as you can see here the character is here and the thing it's here, the blinker, the cursor is here. So yeah, we're gonna have to add one and set the white and black there and the character is to be at the exact opposite. Right, go. Yeah. I think this is moving the cursor. Wait, actually, why not find this? This shows and word doesn't even crash. Okay, yeah, alright. So we're gonna print the string. Okay, we printed that. Print. Oh, I'm so dumb because we never called this function on the main. Our entry point is never pinged up. So it's gonna be character variable string, pointer string. And it's gonna be an integer save, cursor. Int I so it's 0 while the link sets character at video memory link and offset plus and no plus and offset plus positive and now we're gonna set the cursor at the offset. Alright, so most of the function are done. Okay, so we're gonna handle the line scrolling. Okay, we're gonna see that video though. So let's handle the new line characters and it's gonna be an integer function. We can insert state divided by 2 times max column and int get offsets. Now we offset int call and int scroll. So we're gonna return 2 multiplied by row times max column plus column. Right, that'll be for these two functions. So we're gonna combine these two functions to easily write the next part from the say next line integer offset to 9 offset return set. We're gonna the row is gonna be the column is gonna be 0 to the right, the y-axis and the x-axis to the row gonna be get no from offset, and then it's gonna be no say and it's gonna be plus 1 Very good. And print string is gonna be updated. Thing string I string E. Okay, there is now a string I is I. Okay, then the line is a string. Offset is gonna move set the new line offset and else we're gonna make this here. Yeah, I think that's it. Yeah, and string as soon as the message since the maximum value should slow down without slow buffer to apply will those but this is okay for now. We can place running by exceeding the point state. Move all of by the first by one upward. We don't need to move the top row once it will be out of bounds anyway. Do the last row is blank, square rate offset inside our grade bound. Okay, let's see how it works. Alright, so we remove one from top and add one to the bottom. Like, how many views does this video have? I wanna know, I'm so curious. We can implement the ROM by copying each video memory requests. We will write a function that copies a given number of bytes in memory from source to destination. Alright, so void memory copy character source character destination and then bytes type for I which enter 0 I bytes process in the destination is 1 there's this one that'll be it. I think ordinary copy and yeah, and I will go rerun scroll. It's scroll line whatever. Let's go save memory copy. So after data updates 0 and 1 video address. So something here. Okay, offset and 0 and 1 plus no, it's actually 0 and 0 and plus video addresses. And finally the max columns times the max rows minus 1 plus 2. No, it's times by 2. Sure? Oh, my bad. Or 3 column 0 column max columns plus Select character. Come on. Come on. Let's get the memory. Okay. Offset and call max. No. Max rolls. Oh, come on. So max rolls minus 1. On the right. Maybe we're gonna return offset minus 3 multiplied by max coordinates. So we're gonna update the print string again. So I want zero string I. Hey, it's another if. If states is less than greater than or equals to max arguments. Maybe check this. Not max. Max was and max arguments. And still very easily gonna have to offset go by offset. And I think the rest remains to whatever it was. Yep, it remains. Turn the screen. Okay, so we gotta quit screen, forget about that. Okay. Clear. For drive. Alright. 0 and max arguments, max rows, and we're gonna implement that. No. And we set the character at the video memory. Cursor, get the offset, 0, 0. So the main function is gonna be if this clear this free. Yeah, I can see getting ready with this thing. String. Okay, so now we work with this and new line. Okay, there are some issues. It says slowly can't find this rolling line is probably below. I think I can just copy it out. Move it to the line now. But no, that's not how it is, you know. It is a think. What is it? No. We'll see. Let's see to nearby. It's gonna, yeah, integer new line. Okay, more errors. More in the heading and attack. Oh, next roll is a link line here. So is yeah. So sure, let's go. So we don't see the hello for some reason. Okay, I think we should have wrote this whole thing in something on writers, and we're gonna write this right on page. Is that how it is? If so, then we're gonna have to copy everything. And we don't need to do this. Right, once. I'm pretty sure everything is gonna break here. Very sure. Oh, just how we do it. Good. Let it. Drivers. Village. Alright. So yeah, definitely we've got an issue. And checking down the where could be we work around. Yes. Sure it does. So now our current is very clear. So I don't get it. So we wanna actually be made yeah. Oh come on. While we put it here. I don't usually use GDB, so to be honest. Right. I'm really going to receive a real work driver that always the presidency. I think you're supposed to say this, but I'm not seeing a thing. I didn't see the blinker, but nothing else. Not even the keyboard. What if we never clear the screen? Then I worked. So the print screen works, but it's not the print screen for some reason. And it could be a logic issue. Okay, print screen. What are you gonna look like at the end of the day? So this is how the print screen is gonna look like. So we have to get the cursor. If it's false, so then I'll say, alright, yeah. Then we scroll, then it's the string. Right, then we need to offset in the line. Say, I'll set characters, video memory. Minus set, plus 2, plus and set cursor. Okay, screen works. It's confirmed. No, I didn't see that. We're gonna touch just the remote. If you're running, how are you gonna do this? Yeah, I don't know. Actually, don't answer that. I put some done right now. While I then we run it, then run. I don't know. Okay. Oh, the double check the address. Yeah. So it's a bug in the memory copy. Look carefully. It mirrors I. Infinite override. The same bytes. There we go. So it says should be like this. And actually this is the one that I am able to read. To be honest with you. Make same thing in this row. Yeah, let's play screen.